Hello, I am Robin Lee, and I'm going to explain question A, ascending photo, from the Northwestern Regional Contest 2017. In this question we have a list of people of various heights who have been taken a photo of, and we need to rearrange that photo into ascending order by making cuts into the photo. For example, in this case here, we want to put them in some order rather like this. And we can do that by cutting the photo here, 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 and here. We need to find the number of cuts in a general way. So, the important thing to notice is that we always need to put all items of equal height together in the end. And so, we have a choice of which order to put numbers in relative to the ones with the same height, but otherwise we don't really have a choice. So we can put 1, 4 and 8, all of the same height at the start, in any order. But then we have to put them all before 2, 5 and 9, which are all taller. We have to put those before 3, 6 and 10. And then we also always have to put this number 7 on the end because it's the tallest. But the way to solve this efficiently comes down to the number of pairs of blocks inside of this, where we can match up the number the previous block ends with the number the next block starts with. So, for example, to match up this 7, we could put a 6 directly before it instead of the 10, so that they're in the same order relative to each other as they were in the original list. And then we save ourselves a cut. Similarly, we have a 9 and a 10. We can save ourselves a cut by swapping around the 10 and the 3 here, and saving ourselves a cut. And then, while we can't pair anything up with the 8 because the 9's already been used at the end there, we can swap in the 1 or the 4 to match the 2 or the 5. In this case, we'll swap the 4 and the 8, and also the 2 and the 5. So to start with, in this case, we always know which number to put on the end. And we know with this one option, in this case, that we can always save ourselves a cut by putting the 6 before it, or we can not save ourselves a cut and save the 6 for future use by using any of the other numbers. So we should keep a dynamic programming table of, if I end the block that 6 is in with 6, what can my current score be? So from there, I have the option of using either of the other two numbers in this block to match up with the previous block, which again I can solve by checking each of the numbers that could be put at the end of this block, given the numbers available in the next block. What's the maximum number of cuts I can save? Until I get to the last case, we have our terminal case of not saving any cuts. The problem here is that we can match up numbers at the start of a block, which may be proportional to some number k, with numbers in the previous block, which also have some number of possibilities k, which could be up to n in both cases. And the number of ways of combining them together is k squared, which for a million elements is quite a lot. So we have to find a cleverer way of doing this. Luckily, the number of elements that can pair up with 6 is the same as the number of elements that can pair up with 3, and the costs are almost the same. The only difference is that 3 must pair up with 4, 6 must pair up with 7, and so we can compute all the matchings between one element and the next, or one block and the next. So for example here, we can compute all the matchings between 9 and 10, 9 and 3, 9 and 6, and they come out to 1, well, because we have the 7 matched up already, to 2, 1, and 0 here, because if we match the 9 up with the 6, not only do we lose the matching between the 9 and the 10, we also lose the matching with the 6 and the 7 because it's been moved somewhere else. And we can adapt that for our transitions for the 2, which we can work out as 2 matching up with 10 gives us only 1 because we can still use the 6. 2 matching up with 3 gives us 2 because we can use the 6 and we have a matching of 2 and 3. And 2 and 6 gives us nothing again. So in this case, only 2 values changed. The 9 had a value it matched up with, which increased its score, and the 2 had a value it matched up with, which increased its score. And those are the only elements that will ever change in the transition when going from one item in a block to another item in a block to use at the end. So we can calculate this transition once for the last element, for any of the elements, and we can adapt it really quickly to the other elements, and then move on to the next block, and so on. And that gives us a n log n solution, which will pass.